We study X13Q angular momentum. The trajectory of a particle is like that. It is making a uniform circular motion because omega angular frequency is constant and radius is also constant. And this is a unit radial vector on the xy plane. The axis of rotation is z-axis. Describe the motion of this particle. The velocity of a particle is actually any time derivative regarding the motion that is making a uniform circular motion about an axis, fixed axis with constant angular velocity is nothing but omega cross. This is very, very important. Therefore, for uniform circular motion, velocity is omega cross x. If you look at the X13NQ, it is a proof that omega it is the same as r omega. That's or omega is a theta dot. R omega e theta hat. That is perpendicular to the unit radial vector. The express form is given like that. By making use of the backup rule, this is backup rule, we find that the acceleration of this particle is double time derivative of position vector. I apply this operator twice. So first I apply omega cross to the x, and then we apply this omega cross one more time. So we can make use of this A cross B cross C, the backup rule. Be careful, this is different from this. This is not equal to this. So A backup rule is the expansion formula for A cross, open the parentheses, B cross C, close the parentheses. So the result is backup A is omega, A is omega, B is omega, C is x. A, B, C. A, B, C. So final result is like that. Minus omega dot x minus x omega squared. Because it is on a plane, circular plane that is perpendicular to omega, x is always making a right angle with respect to omega. Therefore, I can remove this term, find that is x is r er, and omega squared, this is scalar. It is always toward minus er. So this is centripetal acceleration that is always toward the center. Angular momentum, orbital angular momentum is x cross p. And what is p? Linear momentum. Linear momentum, time derivative, any time derivative for a particle making a uniform circular motion about a fixed axis omega, that is omega e 3 hat, then this time derivative is always omega cross. Therefore, I can factor this mass out, and x dot becomes omega cross x. As a result, Again, I apply this backup rule to find it. Again, I have a constraint omega dot x equals 0. Vanishes, and what I have is mx squared. Mx squared, because the x is a rotation and the vector on this plane is always perpendicular to each other. This x is nothing but the perpendicular distance vector that is also called the lever arm vector from the axis of rotation. Mass times lever arm vector squared is called moment of inertia or rotational inertia. Okay, and then kinetic energy is 1/2 mv squared, and we know velocity here is omega cross x. Any cross product is AB sine theta and half. This squared is AB squared sine squared theta, and this is 1 minus cosine squared theta. That is a squared b squared subtracted by a dot b squared. Replacing a and b with omega and x, what I find is 1/2 m omega squared x squared minus omega dot x squared. Again, we find that omega dot x vanishes. We have 1/2 omega squared multiplied by mass times x squared. I told you this x on this plane perpendicular to the axis of rotation, mx perp squared equals mx squared. That is lever arm squared multiplied by mass. That is the moment of inertia. So if something is making a uniform circular motion, then the angular momentum is I times omega. Kinetic energy is 1/2 I times omega squared, where I is mass times lever arm squared. Consider uniform thin rod of mass m, of length L, distributed along the x-axis from 0 to L. Compute the moments of inertia about x-axis first. About x-axis. So all of the mass of the particles are distributed along the x-axis. About x-axis rotation, the x per vector is 0 because everything is on this axis. It is impossible to make a distance, non-vanishing distance from the x-axis. So this integrand is 0 all over. Therefore, rotation inertia about the x-axis is exactly 0. Next, we consider this, that is about the y-axis. From y-axis, we have non-vanishing x per vector because we have some mass element of mass dm distributed over x and x plus the dx, small mass, and we have a lever arm vector whose magnitude is coordinate x. Because this rod is a uniform, the mass ratio of total mass to the length, mass of this small element, width of this length of this small element, this ratio should be a constant. As a result, we obtain from this, by multiplying dx both the sides, small mass is expressed like that. Now we substitute this one into the definition of the rotational inertia about the y-axis. Radius per this lever arm squared is this x squared, and mass is capital M over L. We should carry out the integration from 0 to L. This is 1/3 x squared f cubed evaluated at x equals L subtracted by x equals 0 value. Now the answer is M over L, 1/3 L cubed, and single power cancels. 1/3 ml squared is the moment of inertia about the y-axis. And because of symmetry, about the z-axis must be the same as this one. A hoop of radius r, mass m, is centered at r E1 on the xy plane. Okay, we have center here. This is r. X-axis. Discuss the rotation inertia of the hoop about the z-axis. So we can make this kind of plane. This is the z-axis. And x-axis, y-axis, and we have a circle of radius r, something like that. Axis of rotation is this, and this circle is rotating like that. Okay, so we'd like to find rotational inertia of this circle. The same hoop is centered at the origin. First, we consider this case. So we have z-axis. About this z-axis, a circle centered at the origin. Every part has a distance. Lever arm is always r. So all of the masses are having a lever arm vector of magnitude capital R. Therefore, this circular hoop has the moment of inertia about the z-axis, that is passing through the center of mass, that is mr squared. We need to study parallel axis theorem that is given very well in X13. According to the parallel axis theorem, if I know the CM axis passing through the CM, and I know this an axis passing through the CM. If I have another axis that is parallel to this with a distance, in here we have a distance r. In that case, we don't have to evaluate the moment of inertia one more time. Instead, I copied this and copy mass of the particle and multiply the distance, perpendicular distance between the two parallel axes. Because it is mr squared and distance in here is r, the answer is 2mr squared. If I rotate this hoop about this z-axis, then the angular momentum is I times omega. That's it. So because I has been increased in comparison with the case when the axis of rotation passes through the center of mass, we have 2mr squared omega, where omega is the angular velocity about the z-axis, that is the axis of rotation. In addition, kinetic energy is 1/2 I omega squared, and this is I. Substitute 2 cancels. We have reached point mr squared omega squared is the total kinetic energy of the hoop when it rotates about the z-axis with the angular velocity omega. A uniform hoop of radius r, the same thing, centered at the origin on the xy plane. Okay, xy plane, we have xy plane, and origin as at the center, radius r, mass m, rotational inertia of the hoop about the x-axis. Okay, this axis and mass distribution is like that. Okay, what should I do? I did not compute the moment of inertia about this axis. Previously, it was normal to this plane, so we need to evaluate again independently. Again, the distribution is now parameterized by the angle about this x-axis. Let us choose angle d theta, and for any small angle, mass over angle, mass over whole complete angle, that is 2 pi. So we have this proportionality. So mass of this small part is angle over 2 pi total mass. What is the level arm vector? This is the level arm vector. So from the axis of rotation, so this perpendicular distance is r sine theta. So perpendicular distance is r sine theta. We return to the definition of the moment of inertia, level arm vector squared multiplied by mass. Level arm squared is substituted in here, and this mass, still small mass, is substituted. Over vector capital M over 2 pi appears here. We need to evaluate the integral. The constant r squared is factored out, and then we need to evaluate this. I believe everybody can evaluate this integral without difficulty. It is a 1/2. This is average of sine squared over a period that you find this relation. Sine squared 1 minus cosine 2 theta. So multiples of period, this integral vanishes. Because of this, average value is 1/2. So what I find is mr squared, and this integral is 1/2. So this integral is 1/2. So 1/2 mr squared is the moment of inertia of this problem. Thin uniform spherical shell of radius r. Shell does not include inside. So it is a thin surface. Radius r, mass m. Compute the rotation inertia about the shell about the z-axis. Centered at the origin. So z-axis is about this. We have these circles to construct the whole thing. Okay. First, we remember mass. We divide this into small pieces. Mass is surface density is a mass over surface 4 pi r squared. Okay, this is uniform sphere. Mass is this density, surface mass density multiplied by area. The surface or the sphere is parameterized by r squared sine theta d theta d phi. Or we can always express this one in terms of d cosine theta, and let cosine theta runs from -1 to 1, where the sign, negative sign, is absorbed, replacing the order of the upper limit and lower limit of the integral. And azimuthal angle runs from 0 to 2 pi. As a result, if we integrate over the angle of 2 pi, then this 2 pi cancels, and then we have 1/2 mass, and d cosine theta, where cosine theta runs from -1 to +1. Now, this is a mass element. I need to evaluate the small part, integrate it over an azimuthal angle, and we have a small angle difference. Slice this one in this manner and collect everything together. That becomes the integral. Anyway, the perpendicular distance, this perpendicular distance, if I cut it, cross-sectional form is we have angle theta measured from the z-axis, and this is a lever this is r sine theta. So r sine theta squared and d cosine theta, and we have over a factor m over 2. So this is a radius squared, and this came from this and this. Okay, for simplicity, we introduce c that is identical to cosine. So sine squared is 1 minus c squared. D cosine is dc, and we integrate over -1 to +1. Copy everything all together. We carry out the integral. We find that this is an even function. This integrand is an even function, and our range of integral is given like that. So I factor this integral, and below 0, they are identical to each other. I multiply the factor of 2 and then integrate over the region restricted to the positive case. Now this integral becomes trivial, and this one integral trivial. And I have this arithmetic gives 2/3 of mr squared. This is for the spherical shell. One can also carry out the same calculation for the case of the rotation uniform sphere, that is a field sphere. The answer you can follow straightforwardly. The answer is 2/5. This one is 2/5. It's a small one. Why? For example, disc and wire. Wire, mr squared. Disc, 1/2 mr squared. This is small. Why? Mass distribution near the axis of rotation exists, but it is very far away from this axis. So the the magnitude of the rotational inertia depends on the distribution of the mass. Geometry is very, very important. So in the shell, it is usually far away from the axis of rotation, except for this polar region. However, if it is a field, mass distribution is over the whole space. So the effective level arm vector decreases. So factor to fifth is smaller than to third. We can also compute the rotation inertia for a plate, uniform plate. Mass is distributed over uniform plate, and the recent axis of rotation is like that. Minus 1/2 of A plus 1/2 of A minus 1/2 of B and plus. Okay, so it is a kind of rectangle. We have mass M. Axis of rotation is a z-axis. Okay. If you look at this plate from above, an element, this element has the mass, total mass, the total area A, the B, M over AB multiplied by small area, dx dy. This is dx and this is dy. And what is the level arm vector? This is the level arm. So x comma y. So distance from the center is the square root of x squared plus y squared. And level arm squared. So we have integrand that is x squared plus y squared. We need to evaluate the double integral evaluated from x from minus a2 plus minus 1/2 a2 plus 1/2 a, and for the y integrated over this region. It is straightforward to evaluate this integral. The final result is 1/12 mass a squared plus b squared. Okay? Here, factor of 2 comes from the fact that integrand is, what's that? This is even function in x and y. That's it for today. Thank you.